Hello everybody. Welcome to episode 004 of CodeWhile. In this episode, I'd like to share a bit about the timing of timing. What's the cost of timing operations? So we'll explore that in this video here. What I've got here is a web page that you can follow along with. Its address is in the address bar here, or you can scan the QR code you see near the top right of the screen, and that'll bring you to the same web page. I've got some stuff copied into my clipboard. I'm going to paste it into this evaluation field. If you don't know how to build a web page like this one, you can see episode 002 to find out how. All right, let's get started here. I'm going to paste something I've already copied into my evaluation field, and then I'm going to evaluate it. I get an object, and we're going to explore this a little bit at a time here. Let's go near the top. I'm going to show you the top, but then I'm going to explore the functions one at a time with you. So near the top here, I'd like this code to be able to work in any sort of JavaScript environment, not just in a web browser. So the first thing I've done here is I've checked for the type of the window identifier or variable. And if it's not an object, I'm going to assume that it doesn't exist in the JavaScript environment that the code is running in. And I'm going to create an empty object and assign that to the window identifier. The next thing I'm going to do is to create a property called timing tester for the window object. And it's going to be the result of calling an anonymous function, which returns an object. And this is that object in here that we see. The curly brace that begins the object is right here, the left curly brace. And then the object has a properties, an inputs property, and that is another object. And it's got some inputs, things we'd like to specify for our timing testing that we're going to be doing. One of the names is time for estimation test, and I've set it to 5,000, representing 5,000 milliseconds or 5 seconds. Another input will be called trials for finding average slowness of slow exponent. Whoa, that's a long name, isn't it? And it's set to 1,000 trials. And then another input is trials for finding slow exponent, and that's also going to be 1,000 trials. Down here there are some outputs. I've assigned null to all of them by default. They'll be populated by the functions that get executed later on. The outputs are average slow exponent rounded up to a nice integer value, average slowness of slow exponent, and time elapsed for estimation test. What does all this mean? Well, we'll find out here. I'll scroll down a little bit here, and let's start with the find slow exponent function here. I'm going to check just that function in here. Let me do a little bit of typing. Here's just the find slow exponent function. And it has an accumulator, an exponent, an op, power, time 1, time 2. This will be the start time and the finish time. Trial and trials. These are all variables I've declared here. I'm going to set the trials equal to one of the inputs. This.inputs.trials for finding slow exponent. And then I'm going to run a loop. And in this loop, I'm going to set the accumulator and the trial variable both to have the value 0. And the iteration index is going to be this trial, and while trial is less than the count of trials we're supposed to run, we're going to iterate the trial. For each of these trials, I'm going to set exponent time 1, time 2, all to 0, and then while time 2 minus time 1 is 0, I'm going to iterate again. And what I'm doing here, pardon me, is I'm going to climb through exponents for powers of 2 until I find a power of 2 that when I run an operation that many times, it costs more than 1 millisecond. Because once we reach 1 millisecond, we'll have some evidence that the operations, that number of operations actually takes time. So here I assign the power of 2 based on that exponent. It starts at 0 and it climbs its way up. You'll notice there isn't a limit to the exponent here. It's just when it costs at least 1 millisecond that will stop, will break out of this loop. Then I take the start time and then I iterate over the operations here. I start at 0, and while the operation is less than the power that we just established, then I'll iterate. And all I'm doing is taking a new date. And that's the single operation that's happening at the root of all of this. I want to know the cost of taking a timestamp. And this is one way to get a timestamp with a new date. So in this inner loop, that's going to be iterated multiple times until it costs at least a millisecond, till we get a batch run that costs at least a millisecond. So after that, we do the whole thing again and again for each one of these trials, because I'm trying to get an average exponent as well. So suppose the first time I go around, it seems that 2 to the power of 8, or sorry, I should say 2 raised to the 8, that power of 2, suppose running that many times finally costs 1 millisecond. Well, maybe the next trial would yield a different exponent that cost 1 millisecond. So I want to get an average, so that's why I'm doing multiple trials, and I'm doing 1,000 of them based on the inputs that we saw earlier. And so for each one of those trials, I'm going to take that exponent and add it to an accumulator, which was initialized to 0 over here. And after all that is done, all the trials have been completed, and I've gotten at least a millisecond cost from each one of those exponents, those powers. Then finally, I'll take the accumulator, divide it by the number of trials, and that'll give the average exponent that was used. And I'm going to set that into the outputs, average slow exponent. And while we're here, might as well round it up for future use. And so I'll set average slow exponent rounded up to the ceiling math.ceil function applied to average slow exponent. And that's what that does. Then for chaining, I return this so that we can go and inspect this result. And that's what we're going to do right now. Let me type it in here. I'm going to call this function, but then I'm going to look at the result. I think this will do the trick. Now this is going to be very busy, so it's going to slow down the web page. Let's find out what happens here. It took a little while. All right, it found that the average exponent that costs at least 1 millisecond to do 2 to the power of this many, sorry, I should say 2 raised to the 12 would be a decent guess at how many times we need to run new date in order to cost at least a millisecond. All right, that's good. Let's take the next step here. The next function is window timing tester find average time of slow exponent toString. All right, here's the next function. This one is called find average time of slow exponent. Once again, we've got some variables. In this one, I'd like to be able to call this function to begin with and for it to invoke the previous function that we just explored if the results haven't been already established. So first I check for the type of the output that we just checked a moment ago, and if it's not a number, if it's still null, which was what the default value was, then we'll call that function that we just called a moment ago to establish this output. Then next, we're taking that result and we're going to get the power of 2 that is raised to this exponent here, average slow exponent rounded up. Once again, we've got a count of trials. This time it's from the trials for finding average slowness of slow exponent, that long-winded thing. It's also set to 1,000. And I'm going to set the accumulator and the trial number to 0. And while the trial is less than the count of trials, we'll iterate. And for each trial, I'm going to take a start time, I'm going to take an end time, and in between here, I'm going to run new date, once again, as many times as this power. For op equals 0, op is less than power, iterate over op. And after that, I'm going to take the runtime for running that batch, that power count batch of operations. I'm going to take the stop time and the start time. I'll subtract start time from stop time and I'll add it to the accumulator. And this is once again because I want an average. So after all those trials, 1,000 of them, are completed, then I'll store the average time that it took for that batch size, that power's batch size, by taking the accumulator, dividing by trials, and assigning that to this.outputs.average slowness of slow exponent. All right, let's give it a try here. Once again, I'm going to explore the output directly after calling the function. All right, ready to run this. It'll take a while because it's running 1,000 trials and each one has a batch, so it's going to take a while. All right. And so what did this tell us here? The average time for those 1,000 trials of running the batch size of 2 raised to the 12 was 1.187 milliseconds. That was the average time for that batch size for each of the 1,000 trials. Okay, all right, what's the next step here? Oops, that's not what I wanted. All right. Let's explore the final function. The final function is the final function here is test timing estimate. So given that we have a rough idea about how long the batch size of operations 2 raised to the 12 took, 1 point something milliseconds, we should be able to estimate how many operations we would be able to pack into something like 5 seconds. So earlier in one of the inputs I specified 5 seconds or 5,000 milliseconds, and this test timing estimate is going to take what we know, do a little math, and try to figure out an estimate for how many operations we would run to populate 5 seconds worth of time. Let's explore this function here. Here I have an estimate. Op, ops, power, time 1, time 2 are all variables. Once again, if this function was called to begin with, it's going to make use of one of the previous outputs, and if that output hasn't yet been populated, it'll populate it by calling the function that we just called a moment ago. The estimate is computed by looking at the inputs. The time for estimation test I specified is 5 seconds, and we'll divide that by the output from the previous function, the average slowness of slow exponent, which is 1 point something milliseconds. Then we'll establish a power here, 2 raised to the 12, and then the count of operations that we're going to perform is our estimation of how many would fit into 5 seconds times that batch size, that power. We'll take the start time, we'll iterate that many operations, this based on this estimate and the power that we already established, and we'll run a new date. That'll be our operation that we're trying to time here. Many of these will run, hopefully 5 seconds worth. And then afterwards, we'll take time 2, the stop time, completion time, and after all that's done, we'll store the result in this outputs time elapsed for estimation test, time 2 minus time 1. And once again, we'll permit chaining by returning this. All right, well, let's give it a try here. How does this go? All right, this is going to take a while, so let's evaluate it here, and the browser will run this code while we wait. And here, it's finished. Okay, what do we get here? The actual time that was taken for our estimated number of operations that would take 5 seconds landed at almost 5 seconds, 4,875 milliseconds. So it was close. All right, and that's how you can time the cost of timing, or approach the problem anyway. Certain browsers might warn you if they get too busy, if it's been a little while in between when there was some idle time. They might give you a warning. Here we haven't run into that situation, but it could skew results. But I hope this approach helps you out if you want to think about timing. Once upon a time, timing could be fairly expensive to query the clock, but not so much these days. It's okay. All right, I'll see you again in another code while, and have a good day, everybody. Take care.